Good morning.
Good morning.
Good morning, Professor Page. How are you?
I'm fine.
Good morning.
Professor Garrett.
Yeah, I made it.
Great.
Okay, great.
Yes, I'm sorry about the confusion that we had about the timing of our previous meeting.
Oh, I think it was all my own fault. I didn't count right. Weeks were going by like days.
I know exactly what you mean. Must be a characteristic of getting older or something.
I guess.
Time goes by before you know. Also, our schedule has been a bit irregular lately, so I have to admit I haven't been particularly diligent about advertising our whatever date we decide on at the end of each meeting. So I'll try to do that in the future.
Okay, that's good. I just finished that paper. I sent you a copy of it. It was already accepted on ArchiveX, and I submitted it to Advances in Applied Clifford Algebra as they requested. So I'm done with that stuff at least.
Great. But you did say you'd be interested and willing to discuss some of the newer results. I know we've seen previous drafts of it.
Yeah, that's right. We've seen a lot of this stuff, really. Yeah, but I'd like to of course, we'll see what Jesus, Dr. Cruz, I'd like to see what he's been doing since I missed his first lecture.
Yes, okay.
Yes, I can make a presentation, a short presentation of the past subject that we discussed. I hope not to take too much time in the way that Professor Garrett can have enough time for his presentation. Okay.
Well, go ahead and take your time. Like I say, a lot of the stuff you've already seen before, so it'd be nice if we can fit some of this stuff together.
Okay. Okay. But I don't know if you like to start first, Professor Garrett, and maybe after I can take my time for the presentation.
No, go on. Why don't you go ahead? I'd like to see what you've done, especially review the first part, maybe, if you would be so kind.
Yes, I think in our meeting, previous meeting, which you weren't able to attend, Jesus and I basically discussed informally ideas about higher order graph theory,
Okay.
especially what it would mean to be a 2 graph or a 3 graph and so forth. And this is like somewhat different than well, there's some sort of overall sort of conflicting definitions in graph theory about multi-graphs and undirected graphs and the whole and now also this notion of a graph hierarchy, which is something of a sideline for graph theory, but it's sort of inherent in category theory. When you think of graph theory as a foundation for category theory, then the notion of an N graph comes up very naturally.
Yeah. So that's interesting because I think I've reduced my knowledge of graph theory. Graph theory is limited, and I reduced the last section of the paper really concerns graph theory. I try to introduce graph theory, so that will that's what I'll concentrate on when I talk. But I like to, why don't we let Dr. Cruz start, and then what you've just said helps me a lot too. I'll concentrate on the lower dimensional case.
Okay. Please, only one moment. I am putting my files that I need for the presentation.
Okay.
Then, a moment, please.
Yeah, so what I will do is just go to the last section. I did send you the paper, so you'll
Yes,
have it.
maybe I'll just take a look at that, what you sent most recently. Yes, I see it's has a fresh date here, March 6th. So
Yeah, I just finished it. Finally. And it was, I've had a lot of trouble with the calculations. But I think everything is correct now.
were you able to do a lot of it with Mathematica?
Well, Mathematica was a big help because, well, on appendix, I have the table of the first 8 dimensions. And all it is a change of basis from the usual basis of a Lorentz-Clifford algebra to this symmetric basis where the inner product of these null vectors is equal to 1/2. It's kind of a new duality relationship in a way.
Yes. Well, that's good and very relevant, since that was one of the motivations for you, I think, to start this investigation, was extending or evaluating the notion of duality.
Exactly.
Yeah.
And actually, it works out very well. At first, I thought I had to increase the dimension, but everything is just 1/2 now. But I think that has a closely related to graph theory too, these connected graphs. So that'll be interesting to see what Dr. Cruz has to say about graphs. My knowledge of graph theory is limited. Oh, it's a huge subject too.
Yes, yeah, a complete subject in itself. But it's a foundational subject, and so it does come up in many different contexts. I should mention we have another attendee to this morning. You might have noticed that Alan has joined us this morning. He's a former student of Dr. Oshevich.
Oh, okay, that's good. I see is Alan Ramirez.
Yes, he was in contact with Jesus and I over the last week, and asked about whether or not our seminars were still continuing. And so,
well, that's good. That's good.
By all means, more the better. So if you're Alan, if you're there, feel free to speak up whenever you want. This is a very informal meeting.
Hello, everyone, and thanks for having me there. I want to hear only for now. How are you going with the meetings and the topics that you are discussing? And if I have something to say, I will do it. But I'm happy to be here.
Okay, thank you.
Okay, I'm ready now. Welcome, Alan.
Thank you, bro.
Okay, I'm going to share my screen. Um, Okay, this is a short review of the discussions that we have been sustained in the past sessions. Then the idea is the first idea that Professor Garrett presented was going from complete graph to Clifford algebra. Then this is the subject that take to me to this kind of presentation. Okay, first some well-known definition of graph that we need for this. A direct graph is a graph in graph theory is intended like a triplet, where the mapping P defines two mappings S and T. Many of these definitions were taken from the books of Uninkel and Knauer and Knauer. Then frequently I used them for these ideas. Those textbooks are standard books in graph theory. And then I am using the standard definition first for this. Okay, here in the figure, I have a direct graph presented in the standard form. And the normal language that we use here is that V are the vertices of the graph and E are the edges of the graph. Then using the incidence functions, we can build a standard graph, but a directed graph. Okay, then the idea, and this is part of the work that we made in the past with Professor Osiewicz. Here is the presentation of graph like a collection of cells. Then we speak here about cells and start with the idea of vertices like zero cells. Then we build a graphic establishing some morphisms between cells of different degree. Then a directed graph is a morphism between zero cells and one cells.
Just want to interrupt briefly. On my screen, your slide is slightly cut off on the right-hand side. So I'm missing maybe half an inch or a centimeter or so.
I have no trouble.
No, you see the entire.
Yeah, I see the entire screen. 5.1.
But are the words cut off on the right-hand side?
No, I'm fine actually. Yeah, I don't know why you're...
I think you have opened the window for our profiles for our video. Maybe that's why you're having your your screen code. I can see all the presentation.
Okay, some artifact on my system, I guess. Okay, thank you.
Yes, because maybe if I move this, you can see the
Oh, that's worse now.
words now. Okay.
For that's strange. For me, it's better. But yeah, I saw you move it, and I saw like it shifted.
Maybe from time to time I can move the presentation to my left in the way that you can see all the text.
Okay.
Okay. But here are the principal ideas that we use for the building of a multigraph. Then we started here with a direct graph, and then a direct graph is a one graph. One graph is a morphism between one cells and zero cells. Using this process, we can go to the next slide where we are representing some illustration about this process. In the top pictures here, I have first in the upper left corner zero cells that are only a set of vertices, and in the upper right corner I have a picture with maybe I can no okay. Maybe I can make some annotations here. Okay. Okay, I remember. Here we can have one cell, and here we have zero cell. Then the idea is to make one morphism between these two cells, and this is presented here in this picture. Then not all the cells are used. Maybe not all the vertex are used, and we establish one relation that is showing here, and the relations are here presented in this way. Okay, with this we can build different degree of cells, and then we can go to multigraph. Then a multigraph is a n-graph that is a collection of morphisms between different degree of cells. Then here we have here this presented in these equations. Sorry, I can fix this. Okay, in these equations are the different levels of morphisms that we are establishing with the different degrees of cells. Then this is illustrated in the next slide. First, we have a zero graph. Then a zero graph is only a collection of vertex. Now we established a relation between 0 cells and 1 cells, and then we get a one graph. This is the first level of complexity here, and then after we take a second level of relations here between edges, and then we get a two graph. Here we are presented like 0 cells, the dotted circles that we are putting here, and like 1 cells, the arrows, and like 2 cells, the double arrow. Then in this way we get a two graph. Okay, and here this is illustrated to the 3-level graph. Yes, a 3 graph. I don't know if you can distinguish here the difference between the relations in 2 graph and in 3 graph. Then those are the different here. This is 1 cell. These are 2 cells, and here we have 3 cells. Excuse me, somebody is going to say something? No?
Yeah,
Okay.
I'm just trying to understand what your arrows mean exactly. When you have that double line with an arrow on it, what does that mean exactly? Or how do you distinguish between the two? It's just notation, I guess.
Yes, and the notations are this. The BI are elements of one's cell. Then the
0 cell, right?
okay, thank you, Professor. 0 cell. Okay.
Yes.
F, G, etc. are elements of 1 cell.
Oh, okay.
Yes, and the
So F and G represent edges then, or defining an edge then, I guess.
sorry.
F and G denote edges then, basically. Yeah, that's right.
Yes.
Yes, and, but
Directed edges.
But they are higher order edges, right?
yes, higher order edges.
So
Here,
what do you mean? What is a higher order edge? It's just, yeah, I don't understand. What is a higher order edge?
It is to take like an ordinary edge as a source and another ordinary edge as a target. So in effect, edges become nodes, and then you have a new notion of edge, a higher order sense of edge.
Becomes a directed edge then. I would.
Yes.
It's basically a directed edge then, or what I would understand as a directed edge. Then.
Well, but it's critical that you understand this hierarchy of mappings, right? That Jesus showed in the previous graph, where we have Jesus. Maybe could you skip back to the previous one? No.
Here?
This, yes, this one, yes.
Mhm.
Yeah, so what he's denoted here as G0 are ordinary vertices, right? In a normal sense of graph, and G1 are edges in the normal sense of graph, but there's in this sequence there's a G2 and a G3, etc. And these are successively higher order edges, right? So a G2 edge is a relationship between two G1 edges,
Then
etc. Right?
What kind of relationship?
Source and a target.
Okay, you're actually mapping the edges on different edges onto themselves or onto other edges.
In the same sense in which you mapped a vertice onto another vertice with a directed edge, right? So it's a generalization of edge to be of successively higher order edges.
Okay.
For example, we have here those, the elements are B, and here the elements, sorry for, it is difficult to make some
It's fine.
Some notations. Here are F lower letters, and in G2 we have the notation like capital letters, no? And I not remember how we call G3, but is another notations. F represents a relation between B8 and BJ, and A represents relations between F and G, for example. And in higher order, we can have G, a relation between G and H, for example, that are the, I don't remember, but maybe in Greek alphabet, we can show the different orders of relations. Then,
So what would be a complete graph? How would that fit into this idea? These higher order graphs. A complete graph. That's where
complete graph is a higher order graph. Yes, we can see this more in a few slides.
Okay.
And then the notation here is this. This is the notation for this relation, and the notation for this is in this way. In terms of graph, and the zero cells as are dots. B are dots. Then this is the way that the graph is are wielded. and I'm go again. This is 0 graph. Here 1 graph, and we have now 3 kinds of cells here represented: 0 cells, 1 cells, and 2 cells. And in a tree graph, we have 4 relations. Okay, this is the idea with the multigraph. Then, okay, I am going to show to you some standard graph in the literature and show how those are related with multigraph. Then first we go to a complete graph. This is the standard definition of a complete graph. Then this can be illustrated in this way. I am going to move to another presentation here. And here I have a complete graph. Okay, first a no direct graph, a no directed graph, but now we have here a complete graph. All the nodes are related. We are using a standard compensation that frequently are used in the literature. When we use a no direct graph, we at the same time, oh, sorry, here I cannot make annotations, then not possible. But the idea is that these relations that are not directed at the same time can be considered like a two-way relation. For example, one relation between the vertex 1 and 2 and a relation between the vertex 2 and 1. Then it is important because in a complete graph, we have here relations in 2 waves that are equivalent to no directed graph. Then this is an example of a complete graph, and okay, here are some examples of complete graph. And here the idea is to show the different cycles that we can build in a complete graph. Then this is here is a first example. We have a 3 complete graph and a first cycle that are using is this cycle is of long one. Then this is the idea here. Then we have here 2 waves from vertex 1 to vertex 2 and the inverse way.
So all complete means then is that all the edges are connected, but they can be connected many times over, and it's not just an undirected edge, then that's just the simplest case of a complete graph, then I guess. A complete graph can be pretty complicated. As you're saying, all the vertices are connected by two paths in this picture.
Yes, here is too complex, and then we can get different kinds of cycles here, and here we can go in the way that we are complexing more. Excuse me, we are getting more complex cycles.
Mhm.
Jesus, can I ask here also why you do not include like say having the same vertex as both source and target?
A loop,
So-
then that's a loop, right?
Yeah, so you said quickly that you considered that these loops were of length 1, but I would say that they're of length 2, and that the loops of length 1 are cycles that include only one vertex.
Yes, here in this part of the presentation, I am not considering the loops, because remember that we are using different degree of cells. Then vertex and loops are like 0 cells. Then here the 0 cells is illustrated like a vertex. But after, when we speak of graphic like categories, then we are putting explicit the relations, the loops in each vertex.
Ah, I see. So you ultimately you would eliminate the notion of vertex altogether, and so your 0 cells would be loops. Right?
Yes, automorphisms.
Aha, yes, okay.
Mhm, mhm.
Of course, you can have more than one loop, 3 loops connecting to the same vertex. So it becomes very complicated then, I guess.
Yes, here we have sorry, I don't know how to move this correctly or in this way. Okay, now here we have a cycle of that we are including two vertex that are apart. 3, 2. Okay, here's the notation. This notation is incorrect because we have a 3 degree cycle here, because we are we are including 3 different vertex here. Then the trial are not 3, 2, but are 3, 3, 1. Okay, but here, like Professor Garrett says, we have different kind of trials that are showing to us more complicated situations. Here we can see this cycle like one path from the vertex 1 to the vertex 3. In this way, we have a trial T3, 2, and one path from the vertex 3 to the vertex 1 that is in the opposite direction. Then this is illustrated here. Okay. And here, okay, now we have trial three that are included the three vertex, but the travel is from one the vertex 1 to vertex 2 and to vertex 3, and the opposite travel now are from the vertex 3 to vertex 2 and vertex 1. Then these are different from the prior trial. And finally, we have one more here that are going directly from the vertex 1 to the vertex 3. The vertex 2 are not included, and the opposite travel is from the vertex 3 to the vertex 2. After we are going to connect this complete graph with A3, and then we can show in that graph the different kind of paths that we can build in these graphics. Okay, here one more that is going directly from from vertex 1 to vertex 3, and the opposite is from the vertex 3 to the vertex 2 and after to the vertex 1. Okay. Okay, one more, but now including a travel with the vertex 2, but first we go from the vertex 1, vertex 3, and we go back to the vertex 2, and after vertex 3, and go back to the vertex 1. Okay, this is the, I think that it is the last, yes, the last picture here. Now I go back to the presentation, and we go to another kinds of graphics. Here we have the definition of a tree, then a tree with vertex have those properties. T is connected, T is acyclic, and T has n-1 edges. Then this is illustrated here.
So far it looks like you have only a classification of graphs, but I guess you're able to do some types of calculations as well.
sorry.
It looks like right now we're just classifying graphs, different types of graphs, but then finally you need to be able to do calculations as well, I suppose, or somehow relate these ideas together.
But I have not here calculations yet. See the tree graph.
Okay.
But okay, those graphs are obtained by a calculation on Mathematica, but not. I have not here all the detail of these calculations. Then here we have first illustration of a tree graph. Then a tree graph is a hierarchical illustration. In fact, that is presented here is a rooted graph, excuse me, a rooted tree. Here, the root of this graph is the node 1, and the other nodes are related with the 1, and those are in a higher level. Here, higher is to the bottom of the slide. Then this is a tree graph, and here we have a higher degree of trees. Here is a tree of degree 6 that is only going back in the in this kind of relations. Then the node 1 is the root. Node 2 are in the first level. Node 3 is the 2 levels, and so on. Then the idea is that we have here, for example, a complete tree that is from a complete graph. This is obtained only with the trails in a complete graph in only one directions. For example, if we consider going in the graphics from one vertex to another, and we define this like one weight 1, where weight is associated to the edge, then we can define this like the direction of the relation. Then here we have only presented the trials in the complete graph that are of weight 1. Only that, not taking the travels in the back direction.
Yeah, this looks like a family tree, a family from one individual going down different generations.
Yes, here the idea is that we can build this tree like a family of trees. Then in fact, in the expression that we use it for building it, you can see that those are recursive relations here for building different kinds of degree trees. Okay. We can connect a tree like a multigraph. Then here's we have a zero graph that is equivalent to a empty tree. This is the first level. Here are the I don't see the graph, the output of the graph here, because we must to have here one node, but I don't see in this graph. I hope not a problem with the next. Okay, in the first one, I have if I build a tree with the GO, then I get the graphics of degree 1. Sorry, it is not clear, the pictures. Maybe you can see, but this is not good representation. Sorry, in the Mathematica file, it is we have a better presentation, but not here. This. Okay. Okay, here we have G2. Now you can see here how we can present the two-level tree, and this two-level tree is built with a graph of lower degree. Then the graph 2 is built with the graph of order 1 and graph of order 0. Okay, here we have a higher order graphics, a tree with 3 levels, and that corresponds to a 3-degree graph. And here we have G4, and finally it is not works properly. Okay, I think that is the last, but the idea was to illustrate for a complete graph of degree 6, and then it is needed one more step where we included the G4, but not in this presentation. But maybe we can think in this like a complete graph of degree 5. not degree 6. Then the idea is that we can build the complete graph with 2 trees in going in different in different directions. Okay. Then another important graph is the opposite graph. This graph is built only inverting the functions that are related vertex and edges. Then an opposite graph is a graph built going from edges to vertex, inverting the order of the target and output in the graphics. Then those are the principal types of graphs that are that we are going to use. And here we are starting a relation the graph with binary relations. Then first, a binary relations is a direct graph. Those are isomorphic. Then a binary relations like a set is a subject of the Cartesian product. In this way, we start a relations graph with graph with the binary relations in general. Then, okay, we can think about in general binary relations and direct graph that included here equivalence relations that are reflexivity, transitivity, and composition. This make this give to us the opportunity of represented some important operations here because reflexivity in relations is related with identity, transitivity with compositions, and the composition is associative. Then we have here some properties of these operations, and in sorry, okay, no more here, and then now we have it's possible to relate graph with the category theory. Then here we are presenting the vertex like loops, and then we have here a direct graph that is a first order graph like a category. Then here the one cells are morphisms and zero cells and are zero morphisms. But this is a representation of the property of that define a category. Here we have
Jesus,
yes.
sorry to interrupt. Perhaps I'm having trouble again with my computer, but I see only an original graph that says G1 without.
Yeah, that's what I see too.
So I don't see what you are
Talking
would-
about.
Yeah, I don't see the slide that you were discussing.
No.
No, I see only, it says G1 equals the tree over G0.
Oh, and maybe I need to interrupt the presentation. I'm going again.
Yeah, okay. And then start to share again.
Yes, because some problem maybe.
Okay,
Now,
yes.
oh, sorry, I don't know where this presentation was interrupted, but the idea here is to relate graph and binary relations. And like part of this, we arrive here to the concept of category. In fact, category is considered first like a graph. MacLean used the concept metagraph. A metagraph is built only with vertex and arrows. And then with this metagraph, we add the concept of loops that are the identity, and then we add the composition in the graph. Then here, for example, H and K that are morphisms are representing the composite relations K and H. First H after K. Then this is important because we have here different kind of commutative diagrams. For example, here I am drawing this apart. We have here H. Maybe first here the vertex that in category theory are called objects, and H and F are called morphisms. Then we have here first H after K, and then if we have one relation here, we speak here about K first after, sorry, first H after K. The composition of these two morphemes. But here we add the identity. Then if this is the object O, then I have here the identity IO, or like in the picture, like IBO. Here we have whatever between. Then this is IB2. Then here we are adding this kind of operation that are composition and the identity. And in this way, we speak of a category. Then I think for the moment, I only have arrived to here. But this is the principal ideas.
So is it wrong to say that category theory in a certain sense is a representation of graph theory, or you can represent graph theory with category theory, or some deep relationship between the two?
Not all graph representation is a category. No? Graph representation are more general and maybe can be more complex relations. In category theory, we have some restrictions about the kind of relations that we can build here. First of all, those are direct graph, because those are binary relations, but with identity and with composition. This is the principal ideas in for starting a category.
So you could say that a graph is a kind of pre-category. Right? It has the same structure as a category, but it doesn't have the axioms associated with composition.
Yes, yes.
So did graph theory inspire, in some sense, category theory, or I don't know the history of category theory really.
I think that the history of graph theory is more older. In the 19th century, I think that there are many works in graph theory.
You mentioned MacLean, and I think one of the concerns that MacLean had was that set theory was considered an inadequate foundation for mathematics, but the notion of a graph could, in principle, be defined without the notion of set theory, and that the sort of the foundational idea of what he called metagraph was a kind of replacement for set theory, at least in its most abstract formulation. So he wanted to build the rest of category theory on top of graph theory in abstract, without references to sets at all.
Interesting.
The notion of what originally was called a set is then becomes something that like a structure within category theory of a very particular kind.
Yeah, so so vertices alone you can think of as being a set, but of course these loops. Well,
it's much better to be very precise. It's much better to think of the vertices as being a class.
Okay.
And
you
the
have
subtlety has to do with the notion of number and countability and the axiom of choice, right? Which doesn't apply to a class.
Yeah, then you have these loops, or which are replacing vertices with more complicated structure so that goes beyond set theory.
Well, I wanted to mention these loops because you did, Garrett, you did ask this question about suppose that we have many different loops on the same vertice. Right? So this notion in category theory here is adding something in addition to that, is these morphisms that go back to themselves or automorphisms. Of the automorphisms, there's one distinguished automorphism that is referred to as an identity. And it's distinguished in the sense that it interacts with the notion of composition in a very specific way. Right? It's the identity for composition.
Yes, for example, we can write here H first after I. B2. This is equal to H. This is the property of identity, but we can have, like Professor Page says, another kind of automorphism. For example, S, and then S composition to H not is different from niche.
Yes.
And then S is not an identity. But identity have this property.
So does Ojevich's book use graph theory as an introduction to category theory, or does it relate category theory a lot to graph theory?
No, because here there are different kind of problems. We can use category theory for speak about graph, but then if in fact this book that I refer here, where is this? Knauer and Knauer. I don't show this here. Or I think I will not put yes, is the third reference here. They present here a graph theory like a category. Then it is too much interesting, and I hope to use some of the ideas in this book for connecting with Clifford algebras. but maybe it's necessary go more in the way of discussing category theory and in the use on graph theory.
Okay, I noticed in this second to the last reference, algebraic graph theory morphoses monoids and matrices. So matrices do play a role there.
Yes.
Of course, that ties it immediately to Clifford algebras, since any Clifford algebras can be represented as a isomorphism to a matrix algebra.
Yeah.
Or
I think that if we use this presentation of graph theory, then we can abord in interesting way the subject of Clifford algebra. But I hope that in a future presentation I can speak more about this.
okay, very interesting. That helps me a lot in what way I'm thinking about these ideas.
Okay, I think that's a very good introduction. Yes, and I think it's appropriate now. I think we still have time that Dr. Sojcik could perhaps summarize the new work in his paper.
Yeah,
that he
it
just,
does give me a
published.
direction what I can concentrate on. The relationship of Clifford algebras to a particular class. Well, I only try to talk about complete graphs now because I have noticed now there are just so many different ways of thinking about graph theory, and loops and the rest of it is much more complicated structures, more appropriate with category, or more unified by category theory. So, okay, so shall I share screen, or maybe someone else wants to
Yes.
comment?
No, please go ahead.
All right, let's see if I can do it here.
That looks fine.
Okay, so I did keep my original title, more or less. I added a little bit. Maybe I talk about geometric algebras of light cone projective graph geometry. So I think there's a very deep relationship between these ideas in graph theory, which is, well, I'll just go down to it. So you're all familiar with this introduction or the abstract. It's changed a little bit. But basically, I concentrate on the Clifford algebra G1n, a geometric algebra of a Lorentz metric. That seems to be the closest relationship then. Okay, so let me go through the different sections. So basically in section 1, I show how the geometric algebra is 1, n and n, 1. So this geometric algebra is generated by one vector with square +1 and n vectors with square -1. Whereas this one is generated by n vectors with square +1 and one vector with square -1. So just have a completely opposite signatures, 1n and n1. And I call them positively or negatively correlated null vectors. In the case of G1n, the inner products can all be chosen equal to +1/2. And the inner products of these null vectors can be chosen to be -1/2 for the geometric algebra of the signature n, 1. So I'm not going to really talk about the geometric algebra 1n. So in a certain sense, all we're doing is we're picking out a particular kind of basis of the geometric algebra 1 comma n. So we have n plus 1 null vectors. That means vectors which have square 0. And the inner product, we're assuming, is equal to 1/2. And I'm going to show you how to construct such a basis for this geometric algebra. In section 2, I introduced the basic algebras of linear algebra in Rn plus 1. Normally, in using geometric algebras to talk about linear algebra, we use the Euclidean, just Rn plus 1 with a Euclidean metric. But in this case, I'm going to use the Lorentz metric 1 comma n, where the null vectors are assumed to have inner product 1/2. So very important is in doing these calculations, for example, the trace of a matrix and so on, it can be defined in terms of the so-called vector derivative nabla. So section 2 of the paper then is concerned with linear algebra with this vector derivative nabla. So the metric really is not important in determining nabla. You can determine it with the Euclidean structure, or with any quadratic form. The vector derivative is really defined independently of the signature of the geometric algebra we're associating with Rn or Rn plus 1. So section 3 then considers only the most lower dimensional geometric algebras. In fact, that's what I'll really talk about today. In particular, the geometric algebra. Well, this actually is a mistake. It should be 1 comma 2, not 1 comma 3, but because 1 plus 3 is 4, so that should be really a 2 there. I should correct that. Okay, and then section 4, I introduce barycentric coordinates, and that is where I introduce complete graphs, are studied in which every pair of vertices is connected by an edge. But I don't say directed edge, so I'm thinking when you take the inner product of 2 edges equal to 1/2, that means the edge is connected by an edge, and that's all I mean. I'm not talking about loops or anything, just a complete graph with a simple edge connecting every pair of vertices. Okay, and then I define by sets of n plus 1 null vector basis, a1 to n plus 1, in g1n or gn1. Okay, but I'm only really going to consider g1n, because if you want to consider this geometric algebra instead, you take the inner products of all these null vectors equal to minus 1/2. But I'm going to do the simplest case of plus 1/2. So, so basically, we're looking at a structure, what I call fundamental sequences of successively larger geometric algebras. So we have R, the real numbers, subset of the geometric algebra 1, 1, 1, 2, 1, 3, and so on. So in each case here, we're adding an additional null vector, A, which I call A1 up to AN plus 1. Okay, and they're all subsets of this general set of all null vectors which have the same multiplication rules as the usual rules of matrix multiplication. So you take set of all null vectors. We are saying that they're null vectors, which means they have square 0, but we also assign the fact that given a pair of these null vectors, they all have the same inner product, in this case 1/2, and that's for this basic sequence here. If instead you wanted to consider equal to minus 1/2, then we consider 1, 1, subset, and so on by adding these successive null vectors to the structure then. Well, some references there. Okay, so actually the whole concept, so I'm saying we're really just choosing a new basis of null vectors for the geometric algebra 1, n, or Clifford algebra 1, n. So we're assuming all pairs of these null vectors are in this case equal to plus, well, here's a multiplication table then. So if you have any two distinct vertices of a graph, I'm going to use these multivectors or these null vectors to represent the vertices of a graph. So AI and AJ are two distinct vertices. And then this is the way you multiply them together, which is why I was asking Jesus about calculations. In this case, we're just using the underlying structure of the Clifford algebra for doing basic calculations of a graph then. Okay, so AI squared is equal to 0, AJ squared is equal to 0, and the multiplication AI times AJ it's all really determined by this basic relationship here. AI dot AJ is equal to 1 minus delta IJ divided by, I'm going to choose it equal to plus 1/2 because I'm only going to be looking at the geometric algebras 1, n. So we have this multiplication rule. And with this multiplication table, the geometric algebra G1n is completely defined, which I think is, I guess it's not really so amazing, but it's a way of characterizing geometric multiplication without defining, for example, what is a bivector, trivector? Well, a bivector is still the outer product of two of these null vectors and so on. Well, we'll see a little bit how it works now. So for a set of positively, we're going to only talk about positively correlated null vectors, A1 to AN. We define the sum, AK, capital AK, equal to the sum I equal to 1 to K of the, you can think about these as being vertices. Well, usually I use M8 up to AN plus 1. And I guess I'm doing that here. Yeah, GN1, 1N. The new bases that we're considering of this geometric algebra consist of A1 up to AN plus 1. And it defines exactly the same structure of the geometric algebra 1N. It took me a while, quite a while, to understand these relationships. All we're looking at is a different basis of the geometric algebra consisting of E1, F1 up to, so all these, this is an orthogonal basis, E1, F1 up to Fn, orthonormal basis of this geometric algebra. That just means that E1 squared is equal to plus 1, F1 squared equal to minus 1, up to Fn squared is equal to minus 1. We call that the standard basis of anti-commuting orthonormal vectors. And there you have it. So now I'm going to define exactly what these null vectors AI are in terms of the standard basis of the geometric algebra. So we have 1, E1, F1. Okay, I call these canonical forms of the standard multivector basis elements. So this is just 2 to the n plus 1 dimensional Clifford algebra generated by one unit vector which has square plus 1 and n unit vectors which have square minus 1, and they're all anti-commuting. But it's equivalent now to the same structure. Okay, now I'm going to define, in this case, the standard. Okay, I'm going to show how to get this new basis of A's, of null vectors for the same geometric algebra 1n. So we define E1 equal to A1 plus A2. And I define that, so I'm defining using this set AK as the sum of the AIs from 1 to K of these null vectors then. Now I give a complete relationship in Appendix A, which I'll flip to later on so you can see. But here you have the definition then. So alternatively, the geometric algebra 1 comma n can be defined by extending the real number system by n plus 1 null vectors. That means vectors that have square 0. And so it's just a new basis for the same geometric algebra. A1 is a set of positively correlated null vectors satisfying the multiplication table 1. And now relating the two bases, E1 is equal to A1 plus A2. Well, in terms of the capital A, it's A2. F1 is equal to A1 minus A2 is equal to A1 minus A2. And for all k between larger than or equal to 2 and less than or equal to n, Fk is equal to alpha k times ak. Again, that's a sum of these vectors, A1 up to ak minus k minus 1 times ak plus 1. Okay, where alpha k is equal to a constant minus the square root of 2 times k minus 1. It was very difficult for me to find this basic relationship, but after that, then this alternative basis of G1n is simply defined by the A's, which have that strange multiplication table, which I showed you in table 1 here. So that completely determines the structure of the geometric algebra 1 comma n. Again, so that's very important formula. Now, if I just flip to the appendix, we can see, well, okay, we'll go on here first. So this is called the canonical form. So we can always, we can always order the elements of this geometric algebra by a scalar, and then the vectors, the null vectors, A1 up to AN plus 1, and then we take the product of all pairs of these null vectors, AI, AJ, where 1 less than equal to I, less than J, less than N plus 1. That defines all products of pairs of these null vectors. And then we have triples, and then up to the final, all the A1 up to AN plus 1. So that's going to define the N plus 1. If you take the outer product of A1 wedge up to AN plus 1, then you get the pseudoscalar element then. Well, then I define the other bases, but I'm not going to talk about that, so I'm not going to go into that. But the only difference in the multiplication table is that you replace, well, you can see AI squared is 0, AJ squared is 0. Take any distinct pair of those vertices, if you want to think about it in terms of a graph. They're all null vectors, so they all have zeros. And then you can see AI times AJ is 0 because you have AI squared, that's 0, so it's 0. But on the other, if you multiply AI times AJ is just simply AIJ. But if you multiply AI times AJI, you get minus AI. So in the other table 1, you got AI, okay? And then it's a very simple table. Yeah, very simple but again, we're only going to use this table 1 here. And where is that? Where's table 1 here? That's table 2. Okay, so again, AI times AJAI is just AI then. So if you sandwich AI times AJ times AI, you just get AI back. In the other table, you have a minus here, but that's the only difference between those two tables. But again, the actual definition is exactly the same. Fk is, but now you define E1 equal to A1 plus A2, and F1 is equal to A1 minus A2. So it's just, but basically it's the same table, but I'm not going to talk about that. Well, in this case, again, everything's defined exactly the same. Okay. Okay, so now I show you how to get some of these relationships. basically what we're interested in doing is relating the two bases, which I've defined now. And I relate them by, I'm writing the standard basis of X as a row vector of scalars, S1 up to Sn plus 1. These are just real numbers. Think about a row matrix times a column matrix. In this case, the column matrix is E1, F1 up to Fn. So again, it's just S1, E1 plus the usual matrix multiplication, but now we're using the column vector of a column matrix of the basis vectors, the standard basis E1, F1 up to Fn. And now I'm going to say that's equal to F1 up to, that's the basis using this new basis A1 up to An plus 1. So instead of writing this, I can abbreviate it by writing X. The position vector X is the row vector of coordinates times the, what I'm calling Fn plus 1 of the basis vectors of the geometric standard basis, E1, F1 up to Fn. Or in terms of the other basis, we use X1, A1 plus X2, A2 up to Xan plus 1. That's the other basis. And I'm going to relate those bases now by taking the column vector, taking the transpose, so it becomes a row vector. F transpose of n plus 1 is just E1 up to Fn. And I'm dotting that into this. And that's what defines the quadratic form of the algebra. And you can see the quadratic form is just 1 minus 1 down to the minus 1. Okay, that's the quadratic form of the geometric algebra G1n. Okay, where F transpose n plus 1 denotes the row transpose of the column Fn plus 1. Okay, well, I'm showing how to represent the product of two vectors in the geometric algebra 1n in terms of the standard bases. Okay. Well, then we look at that, and it just, again, I'm considering module the matrix algebra over the module of elements in the geometric algebra 1, n. So you can see these are just the orthonormal bivectors of the algebra. So E1, F1, E1, F2 are just all the bivectors of the algebra G1, n, written as a matrix. But it serves also as a way of defining the product of two vectors in the geometric algebra 1, n then, in matrix notation then. Okay, note that if I take E1, F1 up to Fn, I write E1 minus F1 up to minus Fn. I take the dot product of that using, again, matrix notation, that this is just a representation of the standard n plus 1 cross n plus 1 identity matrix. Why? Because E1 dot E1 in the standard basis is just 1. E1 dot F1 is 0, and so on. So that's just a representation of the identity matrix, n plus 1 cross n cross run identity matrix then. But that gives us the transition matrix T between the usual standard basis S, what I'm denoting as a row vector, times, in terms of the coordinates, in terms of the A basis, times the transition matrix. So that's defined by the Gramian of, you take this new basis, A1 up to An plus 1, you dot it into the, what I'm denoting as the inverse, because why I call that the inverse? Because we saw that that's just the identity matrix right here. So it makes sense to denote that as the inverse of the column vector then. So again, now this transition matrix then is written as a Gramian of these inner products of AI dot Fj. Okay, so I'm not going to, but now you see I want to define instead of calculating in terms of the standard basis, I want to go to the A basis in this representation of the geometric algebra in terms of what I call the A algebra of correlated null vectors plus n plus one of them, okay? Okay, and then we do the same thing as I did for the standard basis. We get a matrix of pairs of the null vectors, A1, A2, A1, A3, and so on. And you can see I'm now representing the geometric product of two arbitrary vectors in the geometric algebra 1n in terms of this basis of A's, of null vectors. And you can see it has, well, in this case, you see A1 dot A2 is equal to 1/2. All the inner products of these vectors are equal to 1/2. So, which is pretty strange. So this matrix is just the identity, well, zeros down the diagonal. And then if you take the inner product of these things, it's all equal to 1/2. Okay, so that's unusual. Okay, now I talk in terms of bivector endomorphisms in this AN plus 1. So I'm now going to talk about the geometric algebra G1n in terms of these null vector bases then. But I'm not going to say much about that. Well, this is interesting, what I call an LPGGK projection. It's a little bit strange. It's, in a certain sense, it's not really a projection, but I'm using that terminology. So we'd have to talk about that more, but it does define, it is a conjugation. Namely, if you take this hat, what I'm defining as AK hat, remember AK is the sum of K vectors, A1 plus A2 up to AK. If you square that, you'll find it, you can normalize it and have the square equal to 1. It's not hard to prove that, but I don't even include a proof, but it allows me to define a conjugation operation, which I call, becomes a conjugation on the geometric algebra 1n. Okay, and the conjugation satisfies double star is equal to G and so on. It's not hard to show that. But now I define, well, I'm not going to go into details here, but it is in the paper. The paper now is on ArchiveX. You can find this paper as in ArchiveX now, which I just uploaded the day before yesterday. But it has appeared as an ArchiveX file. So okay, so I'm not good. So now I would like to study matrices that has this form. So think about the matrix, which I'm calling, okay, take any element G in the geometric algebra 1n, okay? And we're going to study endomorphisms of the form defined by this matrix G1, 2. So in the real case, you can think about G1ij as just being real numbers. So I'm putting it in between A hat n plus 1 A hat, which is really the conjugation. Well, I'm not going to go into details here, but what I'd like to talk a little bit about is the gradient operator. So the gradient operator in the standard basis is just E1 times partial with respect to the X coordinate, which is I'm denoting as partial S1 minus, I changed the sign of this thing because I want, if you remember, the gradient operator of the position vector has to be equal to n plus 1. And you can, that's why we use the minus signs in here. Well, here we can define it in terms of the basis A1n just by the gradient is a 1 to n of the gradient of xi times partial xi. Okay, so we first define it in terms of the standard basis, which is, for example, in the geometric algebra 1, 3, which is the Dirac algebra, it's defined in exactly this way. with gamma 0, gamma 1, gamma 2, and gamma 3 instead of using the F's in the space-time algebra. Physicists use gamma 0, gamma 1, gamma 2, and gamma 3 as the standard Dirac matrices then. Okay, well now I'm just giving important relationships, summarizing the relationships between the standard coordinates in the standard basis with the transition matrix and showing how that relates in terms of this is just another way of okay, if I multiply by the transition matrix inverse, of course, it just relates the xn+1 coordinates to the Sn+1 coordinates then. And this is giving basic relationships of the nabla, of the gradient operator expressed in this new basis. So it's just that's what's so very confusing about this stuff. These relationships can be very confusing. Changing bases is always confusing, and that's no exception with using this rather unusual basis of null vectors. So I'm not really I don't really offer many proofs here because, again, it's just changing bases. So who wants to go through proofs of changing one basis to another? It's not really, but they're pretty straightforward, but you have to keep the ideas straight. It caused me a lot of trouble to get these relationships straight because you can easily get confused with the AIs, again, all have inner products equal to 1/2, which is unusual in itself. Okay, so the idea, okay, so if we can relate the pseudoscalar elements, so again, if you take the standard basis, you take the outer product of all these standard basic elements, you get E1 wedged. Again, we don't need any dots in here because this is an orthonormal basis, so it's E1 F1 up to Fn. That's the pseudoscalar element, the unit pseudoscalar element. And here it is represented in terms of the outer products of the null vectors, A1 up to An+1, while with this factor. Notice that this factor is just the reciprocal of the factor which I called alpha k, which is interesting. Okay, so now I'm giving decomposition formulas for the gradient operator. Again, it took me a long time to understand these relationships, but they're really pretty simple. So what we do, I define the dual end sum of AI as a null vector. Well, I take the complement of AI in the algebra of n+1 null vectors. So again, all we have to do, we take a sum, A1, leave out one vector AI and go up to n+1. Okay, so a pretty simple idea. But again, rather than having to write A1, okay, so this leaving out the ith term of the basis null vectors in An+1, that's all we're doing here. Again, you have to be careful not to get confused by notation. Okay, calculations. Now what I'm doing is relating the standard nabla expressed in the basis An+1 plus can be simplified using the following decomposition formulas, defining the dual sum in null gradients. So I'm decomposing the standard gradient operator in terms of these two new gradient operators, which are defined by, I could call it upside down hat. Where we just take, again, remember this is representing a sum of, so this is leaving out the ith term, the sum of all those vectors times partial I, partial AI, with respect to the AI coordinates. And the hat is just the sum AI times partial with respect to the AI coordinates then, okay? And then we can represent the standard, the nabla of the geometric algebra 1n in terms of the basis then, An+1 times, okay, again, a little bit strange notation here, What do I mean by partial n plus 1? So what I'm doing is taking the partial derivatives I equal to 1 to n plus 1, the sum of all these partial derivatives, and just the straight sum. And again, you can represent it. Again, I'm just giving a bunch of formulas relating the gradient operator. Took a long time for me to understand these relationships, but when you come down to it, well, they're pretty nice formulas. But I just give the relationship, but I don't offer many proofs. Okay, verification of above formulas which are omitted depend heavily on the combinatorial-like identities. Again, if you take A, remember an plus 1 is just the sum of all these null vectors, a1 plus a2 plus up to an plus 1, and you square them all. And what you get is a combination of n plus 1 things taken 2 at a time. Okay, so, and again, another formula, ai dot an plus 1, again, that's the sum of all of them, is just equal to n over 2 times the sum. Okay, so you can see you have to be careful with these things, not to get them confused. And in addition, if you take the additive duality formula, if you take the sum of all these things, leaving out the AI, and take the sum of all of the AJs, except leaving out the AJ, this is the formula you get then. Rather strange formulas. Okay. Okay, so lower dimensional geometry. So here I'm just looking at A3 plus equal to G12, the simplest case in R3. It's R3 because okay, the algebra A3 plus is the same dimension as n2, n is equal to 2 plus 1 is 3. So that's the relationship. We're taking a new base. These are the algebra of the null vectors for the geometric algebra 1, 2. Simplest case. And that was really all I could. Okay, so we have the pseudoscalar element, I'm denoting by I, is equal to E1 times F1 times F2, has square minus 1. In terms of the AI, it's equal to minus 2 A1 wedge A2 wedge A3. Okay, it's in the center of the algebra. Excuse me. Commuting with A1, A2, and A3. Okay, so we can define E2 as IF1, and that's equal to, if you calculate that using the standard basis, then that's a bivector in G1, 2. Bivector, that's the upper index there, represents all bivectors. And if you take the matrix coordinates of E1, E2, and E3, no, that's just exactly the Pauli matrices, which opened the door to the study of quantum mechanics, as well known, of course. Okay, it has many applications in computer science, robotics, and so on. Also, it defines, okay, this algebra G3 is isomorphic to the even subalgebra of the space-time algebra 1,3, which is the algebra of the Dirac matrices of R4, matrix version known as the Dirac algebra. Okay, so that's the transition matrix. 1/2, 1/2, 0, and so on. Again, that's the inner products then of you can see 1/2. Okay, and T inverse 1, 1, 0, 1 minus 1, 0. They're all very simple matrices. So again, if you want to get E1, F1, and F2 in terms of the A's, you just multiply by 1, 1, 0, and you can see you get A1 plus A2 is E1, F1 is then A1 minus A2, and F2 is minus A1 minus A2 plus A3. So again, these are the null vectors. If you take the inner product of any two of them, you get 1/2, and it defines the standard basis in terms of this basis. Or multiplying by the inverse, you can get A1 as 1/2 of E1 plus F1, A2, and so on, relating the standard basis to the basis of these null vectors then. Okay, the canonical forms relating these vectors, bivectors, and trivectors are, again, you just calculate, do the calculations, you get F1 is equal to minus A1 minus A2 plus A3. Look at the bivector, becomes, if you put it in the standard form, that bivector E1 times F1 is 1 minus 2 times A1 times A2. The bivector E1 F2 is this, and then E1 times F2 times F3. If you put it in the standard canonical form, which is defined, becomes A1 plus A3 minus 2 times A1 times A2 times A3. So again, it's just a different representation of that pseudoscalar element in terms of the canonical forms. Notice that A1 plus A3, and then we put it A1, A2, and A3 in that order. Okay, so we can always reduce it to a standard form then. And then I start looking at standard, the simplest endomorphism you can think about as 2 times V1 wedge V. Okay, V1 and V2. I think I define it somewhere.
Dr. Sopcich, I just wanted to mention that we're coming up on 2 hours now, so I just
Okay.
didn't know. Did you want to make reference to graph theory or?
Okay, let's do that. Let's skip over this stuff. It's all in the paper. But it's interesting here insofar as that, okay, so this gives some details that when you represent it in this way, that a vector is represented by a matrix, not a column vector, is in the standard. So that's pretty interesting. But again, vectors are all represented by matrices and not the standard column vectors. But we'll go on instead because I like to talk about the last section. Okay, so this is interesting, but again, I don't have time to talk about it. So let's talk, to get to the graph theory, we start by simplices. Again, I'm using the usual definition here. And okay, so I talk about the content of a simplex and so on, but let's go on. LPGG calculus, okay, I show how to define, okay, let's see. Okay, so now I talk about a signed graph plus or minus where I'm naming the vertices by, okay, so let VM denote the vertices of a signed simplex, okay? So these are just the vertices represented in terms of the standard basis of, well, in terms of the basis of A1 up to AN plus 1 with barycentric coordinates then. Okay, so again, I'm leaving out AI in this notation and linearly independent. The outer product is not equal to 0. VM plus denotes an M simplex with M plus 1 M faces. Each M plus 1 face is geometrically represented by the oriented M vector, which you get by leaving out one of those vertices then. Okay, barycentric coordinates. Okay, a signed complete graph is said to be closed if the sum, when you leave out one of the vertices, is equal to 0 and of order k, if k is the largest number of linearly independent vertices, v plus m. Naturally, we use barycentric coordinates associated with what I'm denoting by S, the simplex S plus n. And without loss of generality, we assume the position vector, again, is given in terms of the x1 up to xm plus 1 coordinates represented in terms of this basis AI. I now restrict attention to studying the graph Vm plus 1 of a particular m-dimensional polytope. And if I square this thing, what I get is 0 less than I less than equal to, well, less than, larger than equal to 0, less than equal to this. You take all pairs of that stuff. So again, I'm trying to define a polytope, and we assume that the vertices are not equal to 0 will all be positive, so that, okay, this is important. So since we're using barycentric coordinates when we're in the interior of the simplex, all these products are positive. Well, all the coordinates are positive. So in particular, xi times xj is positive. So I can define a unit vector then as simply the square root. Since all these terms are positive, the unit vector is well defined. It looks like this is just saying that the vector is in the positive light cone, is what it comes down to, this condition. But so the unit vector is really the same unit vector you get with when you look at the standard unit vector in Rn+1. Okay, and now I simply give a last section of Platonic, what I call Platonic solids. And again, I'm using the specialized nabla. Remember that the nabla in Rn+1 consists of two parts, namely this one with an upside down hat and then the other one. And I'm looking at the specialized one, okay? And if you calculate the Laplacian of that, you get this interesting relationship. And okay, well, and I conclude with this conjecture, which is very hypothetical. I'm not really sure that it seems, from my earlier considerations, it seemed like it's reasonable, but it is a very interesting conjecture. Even if it is false, there must be some relationship that's involved between that and the so-called distinct n-Platonic solids defined by an n-simplex. I give reference to this, which are quite famous references. You can study it in the paper itself. As again, the paper is in ArchiveX, so you can look at the details, and I give references then to the various papers that are involved here. So I guess I can stop there since the details are in the paper. Well, let me just show you the, okay, so this and the appendix A gives you calculates all gives you the transition matrix, which I call T8 for n equal to 7. So we're looking at the geometric algebra 1, 7, positively correlated basis. And you can see A1 in terms of the E1 and F1 is 1/2 E1 plus F1, and so on down the line. Note that it's basically a triangular matrix. So we don't have to redefine. We take A1, A2, and then A3, A4 is just defined successively. We don't have to redefine successive vectors. And this is the inverse of that matrix relating to, okay. And then these classification of geometric algebras, I think, is very, this table that I'm giving here gives interesting relationships, which, well, of course, there are more geometric algebras than I just mentioned, 1n and n1. For any geometric algebra, I think these relationships are important for determining the other geometric algebras, GPQ, defined by E1 up to EP, F1 up to FQ.
So, Dr. Subject, does this mean that you could extend these calculations, this null basis, for any geometric algebra, PQ?
Yes, I believe so. But you might have to, well, yeah, that's the interesting thing with respect to graph theory. For example, I'm saying we have a complete graph because the inner product of any two vertices is equal to 1/2. But of course, if you look at the more general graph, which I call the V's, then you can assign, it can be any, if you just change the sign of one of those vectors A1, I think you can get the other signatures of the graphs as well. So that's where this reference to this last paper I think is very interesting. This one right here, Kovanova, she has written a very interesting paper tying Clifford algebras to graphs, which is also in Archive Ekis, and she relates the usual matrices of edges, connecting edges to matrix theory, and relates it to Clifford algebras in a more standard way than what I'm doing. But I think they're all very much, I think that's a very important paper in trying to understand more deeply the relationship between graph theory and Clifford algebras, which I think that this paper should elucidate as well. So I hope that answers your question.
Okay, so at this point you'd say that you hold this as a conjecture that one could.
Yeah, I'm not really sure about that, but there's obviously a very deep connection between Clifford algebras and graph theory, which I think this paper will elucidates the relationship between G1n and N1 to graphs. But the more general relationship, maybe you don't even have to go. You can define it all in terms of graphs, in terms of these vectors V. I define VI and have everything just as positive graphs. For example, we're denoting the vertices of graphs by null vectors. So you can also put 2 times a null vector is a null vector, or negative 2 times a null vector is a null vector. So maybe you don't have to consider anything but positively correlated bases, and then get the other ones just by loops can be considered as negative numbers or positive numbers times a null vector with positive, it's just difficult to see exactly how all the ideas of graph theories fit in, but maybe you don't have to go beyond the positively correlated null vector basis of G1n. I'm not really certain about but I think this paper by this Russian-American author should be helpful in defining the edge matrices, the matrices of edges connected, and all the other things that people do with matrices and graph theories.
Okay. Just one final question for me anyway. That is, where are you thinking about going next with this work? Or
Well, maybe I'm hoping that Dr. Cruz can help out on this idea. Also, I might mention the work of Timothy Havel. Let me just show you his paper here. Let me see where his paper is referenced here. It's a very interesting paper. This one. He extends Heron's formula from a tetrahedron to a Heron's formula from a triangle to a tetrahedron, and the projective nature of its zeros. I think his paper must be very closely related to my paper on simplices. In fact, so this paper, so these 2 papers, I would say, are very important in understanding a possible direction for going further, in addition to the last reference I give, which is to the seminar which we're participating in right now. I'm hoping that, well, here you go.
You mean the Havel and Kovanova papers? Is that right?
Yes. So I would suggest looking at those 2 papers, and of course, I hope that we can make further progress in how to relate these ideas with what you presented today. Jesus.
Okay. Okay. Mhm. Yeah, I can get those and try to prepare something about this.
Okay, that sounds great. Do we have any suggestions for next meeting?
Well, maybe keep it open again. Let Dr. Cruz go first, and maybe I'll have something to say. And maybe you also, of course, but your comments were very interesting that you mentioned today. Maybe you want to have something to say too.
A first connection of this topic that I saw is with Dirac algebras. There is a paper that about this subject relating graphics and Dirac algebras. Then maybe I think that we can start with this. And I try to review the papers of Kovanova and Havel, and maybe to find some more aspects to incorporate.
Yeah. Your mention of the Dirac algebra, that's the next most complicated case, and that I think that is a good place to start too, right? I need to go to the next level. It's not sufficient just to consider G1-2. We wanted to go at least to G1-3, but of course that's related again to classification of Clifford algebra, because the even subalgebra is isomorphic to the polyalgebra. So in a way, we've touched upon that even today with that simple example. Anyway, I think that's a good idea to start with. So I'll consider that the Dirac algebra case as well for next time.
Okay, shall we continue our current schedule of every 3 weeks? Is that a suitable interval?
Yes, that's good for me.
Okay, I think it's fine too.
So that would mean our next meeting would be on March 29, is that correct? I think so.
Okay. Okay.
All right. Well, thanks very much for being here. Thanks for trying this out, Alam. I appreciate you dropping by. And of course, if at any point you're thinking of something you would like to contribute to the seminar, Alam, certainly you should feel free to do so. You can always send me an email or send an email to Jesus, and we can sort of discuss it a little bit by email in advance. I think that's it for today, unless anyone else has comments.
Yeah, of course, Prof. Thank you very much for having me today.
You're welcome.
Well, thank you for me for very interesting seminar today.
Okay, well, see all of you, I hope, in 3 weeks' time.
Okay.
Bye for now.
Okay, goodbye. Have a nice